Retrieval augmented generation, or RAG, is a groundbreaking architecture that enhances the output of large language models by referencing external authoritative knowledge bases before generating responses. This approach directly addresses the limitations of static knowledge cutoffs, internal biases, and hallucinations that can occur when models rely solely on their training data. By anchoring the generation process in real-time verifiable data, RAG ensures that answers are both accurate and up-to-date. Imagine an HR assistant that can instantly reference the latest company policy updates without retraining. This is the power of RAG in action. Real-world scenarios, RAG systems shine by integrating seamlessly with dynamic information sources. For example, when a company updates its health insurance policy, an internal assistant powered by RAG can search the newly uploaded document and provide accurate answers immediately. This eliminates the need for constant model fine-tuning, saving time and resources. The model retrieves the relevant clauses and appends them to the prompt, ensuring that responses are always based on the most current data available. Chunking is a critical process in RAG pipelines, where large documents are broken down into smaller, meaningful segments. Even though modern language models can handle massive context windows, passing an entire 200-page document directly is inefficient. It leads to high latency, increased costs, and the risk of missing important details buried deep within the text. Chunking ensures that only the most relevant parts are processed, making the system faster and more cost-effective. Consider a scenario where you need to answer a query about capital gains tax limits from a country's entire legal tax code. Instead of processing the whole document, chunking allows the system to extract just the 3 paragraphs that address the specific question. This targeted approach reduces both the time and cost per query, making information retrieval much more efficient and practical for large-scale applications. There are different methods for chunking text. Fixed-size chunking splits text at set intervals, such as every 500 characters regardless of the content structure. In contrast, recursive character text chunking uses a hierarchy of separators, like paragraphs, sentences, and spaces, to split text more naturally. This preserves the integrity of sentences and paragraphs, ensuring that meaning isn't lost during the chunking process. Imagine a fixed chunking method that splits text exactly at character 500. It might cut a sentence in half, making it difficult to understand. On the other hand, recursive chunking would split at the end of a paragraph, keeping the sentence intact. This difference is crucial for maintaining the clarity and coherence of the information being processed. Chunk overlap refers to the practice of duplicating a certain number of tokens or characters from the end of one chunk at the beginning of the next. This technique ensures that important concepts spanning across chunk boundaries are captured together, preventing the loss of semantic context. It's a safeguard against data fragmentation, especially when information flows across artificial splits. For example, in a medical manual, one chunk might end with a recommendation for treating high blood pressure, while the next chunk begins with medication details. Overlapping the chunks ensures that the relationship between symptoms and treatments is preserved, allowing for more accurate and meaningful search results. Embeddings are the backbone of semantic search in RAG systems. Dense embeddings are high-dimensional, continuous vectors generated by deep learning models. They capture abstract meanings and conceptual similarities. Sparse embeddings, on the other hand, are vectors with mostly zero values, focusing on exact keyword matches and frequency. Each type has its strengths depending on the search needs. Suppose a user searches for feline illnesses. A dense embedding will match document chunks discussing cat diseases due to semantic similarity, while a sparse embedding will look for the exact words feline and illnesses. This dual approach ensures both broad and precise retrieval capabilities, depending on the context of the query. Structure-aware or syntax-based chunking strategies leverage the native layout of documents, such as Markdown headers, HTML tags, or JSON keys. Instead of splitting based on length, these methods split at logical section transitions, keeping related information together. This approach is especially useful for technical documentation and structured data. In parsing a technical product documentation page written in Markdown, a structure-aware chunker ensures that a subheading and all its nested bullet points are bundled together. This prevents instructions from being separated from their titles, maintaining the logical flow and usability of the information. Semantic chunking uses machine learning or distance metrics to find natural breakpoints in text based on meaning. By calculating the similarity between sentences, the system splits the text only when there's a significant shift in topic. This ensures that each chunk represents a coherent idea, making retrieval more accurate. For instance, when processing a podcast transcript, semantic chunking detects when the conversation shifts from early childhood education to venture capital investing. The text is split at this transition, ensuring that each chunk remains focused on a single topic for more relevant search results. Parent document retrieval, also known as small-to-large chunking, involves splitting a document into small child chunks for precise searching and linking them to larger parent documents. When a query matches a child chunk, the system retrieves the entire parent context, providing the language model with comprehensive information for generating accurate answers. Imagine a financial analyst asking about the growth rate in Q3. The system finds a matching sentence in a multi-page financial report. Instead of just returning that sentence, it retrieves the entire table and surrounding paragraph, ensuring the analyst gets all relevant context for their analysis. Retrieval bottleneck is a critical limitation in RAG pipelines. It occurs when the quality of the data retriever restricts the system's overall performance. If the vector database fails to surface the most relevant information, even the most advanced language model cannot generate correct answers. Ensuring high-quality retrieval is essential for effective RAG systems. For example, if a customer asks a support bot how to cancel their subscription, but the retriever returns irrelevant chunks about privacy policy, the language model won't be able to provide the correct instructions. This highlights the importance of precise and relevant retrieval in RAG architectures. Grounding is the practice of ensuring that a language model's output is strictly based on the facts provided in the prompt context. This is enforced through system prompts that instruct the model to rely only on the supplied information and to avoid using its pre-trained knowledge when the answer isn't explicitly available. Typical system prompt might say, "You are a factual assistant. Answer the user's query using only the text enclosed in context tags. If the answer cannot be explicitly derived from the text, reply with 'I do not have access to that information.'" This approach ensures that the model's responses are always grounded in verifiable data. Mathematically optimizing chunk sizes involves running a grid search validation workflow. By creating a synthetic evaluation dataset and testing various chunk sizes and overlaps, teams can calculate retrieval metrics like context recall and precision. The goal is to find the smallest chunk size that maximizes recall without sacrificing performance. For example, an e-commerce engineering team might discover that a chunk size of 512 tokens yields a 94% retrieval accuracy, while 256 tokens drops accuracy to 61%. This kind of analysis helps teams balance accuracy and efficiency in their RAG pipelines. Biencoders and crossencoders are two approaches for computing similarity between queries and documents. Biencoders embed queries and documents independently, allowing for rapid similarity calculations. Crossencoders, however, process the query and document together, resulting in higher accuracy but at a greater computational cost. In practice, a production system might use a biencoder to quickly narrow down 1,000,000 documents to the top 25 candidates. Then, it applies a crossencoder to these candidates for a final, highly precise ranking. This hybrid approach combines speed and accuracy for optimal results. Hierarchical node parsing organizes documents into a tree structure, with chapters as parents, sections as mid-level nodes, and paragraphs as children. This structure maintains relationships between different parts of the document, making it easier to retrieve and present comprehensive information. For example, in code documentation, if a search matches several child paragraphs about API endpoints within the same module, the parser rolls them up and presents the parent module overview. This ensures that users receive a complete and organized summary of relevant information. Metadata filters are structured properties attached to vector objects such as creation date, user ID, or category. These filters allow the database to partition and ignore irrelevant vectors during searches, greatly improving the speed and accuracy of vector indexing. In a multi-tenant corporate application, when a manager from Department A runs a search, a metadata filter ensures that only relevant vectors from Department A are considered. This prevents unnecessary computation and speeds up the retrieval process. Understanding the token-to-character ratio is essential when structuring ingestion chunks. In English, one token is roughly 4 characters or 0.75 words. This matters because embedding models have strict token limits while text slicers often operate on character counts. Aligning these ensures smooth processing. If an embedding model has a 512 token input limit, setting chunk splits at 2048 characters prevents unexpected truncation errors. This simple rule of thumb helps avoid issues at the API gateway and ensures that all data is processed correctly. Naive sentence-based chunking splits text at every period, exclamation point, or question mark. The main downside is that it breaks anaphoric references, pronouns like it or they lose their connection to the subject, making the resulting chunks less meaningful for retrieval. For instance, if a document says the Tesla Model Y incorporates a specialized heat pump architecture, it dramatically improves cold weather driving efficiency. Splitting by sentence isolates the second statement. The context of what it refers to is lost, reducing the usefulness of the chunk. Query rewriting is a foundational step in advanced RAG systems. It uses an upstream language model to transform ambiguous or shorthand user queries into fully articulated prompts optimized for vector search. This ensures that the system understands the user's intent and retrieves the most relevant information. If a user types, "How do I fix the error from yesterday?" the system looks at the conversation history and rewrites the query to something like, "Troubleshooting steps for Docker container exit code 137 out of memory error." This makes the search more precise and effective. Document transformation is a key step in the ingestion pipeline. It sits between raw text extraction and chunk embedding, cleaning and enriching data by removing unnecessary markup, translating languages, and normalizing text. This ensures that only high-quality, relevant content is embedded for retrieval. For example, an enterprise web crawler might scrape a company's public knowledge base. The document transformer removes all HTML sidebars, header menus, and legal links, leaving only the instructional markdown text. This high-signal content is then embedded for accurate retrieval. Markdown-aware chunkers scan text for structural indicators like headers and code blocks. Instead of splitting at arbitrary points, they group content logically by heading hierarchy, ensuring that related information stays together. This is especially useful for technical guides and documentation. In a software deployment guide, a markdown chunker ensures that a code snippet block remains attached to the relevant header and bullet points. This keeps instructions and examples together, making the documentation easier to understand and use. Chunking isn't just about splitting text, it's about preserving meaning, context, and usability. The right chunking strategy ensures that information is both retrievable and understandable, supporting accurate and efficient responses in RAG systems. Selecting the appropriate chunking and retrieval strategies depends on the nature of your data and the needs of your application. Consider factors like document structure, query types, and performance requirements to design an effective RAG pipeline. Efficient chunking and retrieval not only improve accuracy but also help manage costs and latency. By extracting only the necessary information and optimizing chunk sizes, organizations can deliver fast, reliable answers without overspending on compute resources. RAG systems are transforming industries from corporate HR assistants to financial analysts and customer support bots. By combining retrieval and generation, these systems provide timely, accurate, and context-aware answers, driving productivity and innovation. Despite their power, RAG systems can face challenges like retrieval bottlenecks, poor chunking strategies, and inadequate grounding. Addressing these issues requires careful design, continuous evaluation, and iterative improvements to ensure reliable performance. Optimizing a RAG pipeline is an ongoing process. Regularly reviewing retrieval accuracy, adjusting chunk sizes, and refining prompts help maintain high performance as data and user needs evolve. Continuous improvement is key to staying ahead in the fast-moving world of AI. Retrieval-augmented generation represents a major leap forward in AI-powered information retrieval. By understanding and applying the fundamentals of chunking, embedding, retrieval, and grounding, you can build robust systems that deliver accurate, context-rich answers. Keep experimenting, measuring, and refining your approach to unlock the full potential of RAG.